Okay, this is problem number 13, 102. We are looking for forces, so we need to draw a free body diagram. So I'm going to draw a free body diagram at point P. So here's the dot for P. It is in a moving in a vertical path, so I'm going to have the gravity on this. Forks and moving in the vertical slotted path. Okay, yeah. So there's gravity on this pin. Mg. Everything is smooth, so there's no friction. The pink slot could be exerting a normal force. I don't know if it's up or down, so I'm just going to draw it straight up like this. We'll call that P for pink. And then there is that that weird shape, the little white guy. What I'm going to do is draw a dotted line to kind of get my bearings on that. So this dotted line is going to come through here at some angle. That'll be that the circular, not circular, but curved path. And it has the ability to apply a normal force to it. So I'm going to call it here. I don't know which way it goes, doesn't really matter. I'm going to call it C for curved path. So that'll be the force that's coming from the curved path, and it's perpendicular to the to this. Now that I have the forces that are acting on this thing, I need to identify the directions that I want to sum forces. And in this case, it seems reasonable with the number of things that they're giving me to plan on summing in the r and theta direction. So what I want to do is identify what the r and the theta directions are. So I'm just going to draw the r direction is from the center of rotation through the point. So it's, in this particular case, happens horizontal. So I'll label that UR. And the theta is going to be perpendicular to this in the direction of positive theta, which is counterclockwise. So the theta direction is going to be actually down in this particular case. So that'd be the U theta direction. So the problem's not too bad, other than the fact that I have this odd angle here that I need to find. So the book likes to call these things psi or whatever it is. So I'm going to do the same thing. So I need to find that angle psi. If I have that, then I've got everything I need to sum the forces. So again, the author talks about that and has a reference. Let me pause this and then I'll find the page number. Okay, the reference is on page 145, and I have mislabeled the angle. So when I look at 145, the author gives an equation for the angle psi, but psi is measured from the tangent of the curve to the UR direction. So let me fix that angle. So from the tangent of the curve, which is shown in the dotted line, to the UR, that is the angle psi. So it's this angle right here that the author has given us a formula for. So he calls that the angle psi. Okay, according to page 145, the tangent of that angle is equal to the radius divided by the derivative of r with respect to theta. Okay. So, in this particular problem, we're given an equation for the spiral, or whatever the thing is called, and it's r equals 0.6 theta. So, the derivative of r with respect to theta is equal to 0.6. So that's equal to the tangent of psi. And so if you take the inverse tangent, so pause for a minute while I do that. Oops. Excuse me. So the derivative I found to be 0.6. Now let me put in the tangent. The tangent of psi is r divided by the derivative. So the r is 0.6 times theta. Theta is 180 degrees, or pi, make sure you put it in radians, divided by the derivative, 0.6. So here the tangent is equal to pi. So if you take the inverse tangent of pi, you have angle psi equals inverse tangent of pi, 72.3 degrees. Okay, so that is the angle between the tangent line and the UR. So the other angle, the one that I really want between the force, this angle here, I don't know, we'll call it beta. Beta is simply 90 degrees minus the 72. Okay, so now that I have all of the angles, what I'm going to do is simply sum the forces. Alright, so from my free body diagram with some forces in the UR direction, P doesn't have any contribution, neither does mg, but I do have the C times the, in this case it would be the, since I'm looking for UR, it would be the cosine, cosine of beta. And that'll be in the positive direction. That's all there is. And so that equals the mass, which is 0.4 times the acceleration. So in the r direction, it's r double dot minus r theta dot squared. If I sum forces in the theta direction, I have minus P plus mg. I also have part of the C, so I have minus C sine of beta. That's it, so that equals mass, 0.4, times the acceleration in the theta. That would be 2 r dot theta dot plus r theta double dot. Okay, so it looks like I have essentially two equations, and if I list out the things that I do not know, or at least right now I don't know, what I would do is I count the C. I don't know that. Beta I found. The R is unknown. I can find it easily, but I also don't know the R dot, the R double dot. The theta is known. The theta dot is unknown, so I don't know theta dot, and I don't know theta double dot. Also, I have a force P, which is unknown. So I've got quite a few. So let's see, that's 1, 2, 3, 4, 5, 6, 7 unknowns, and I only have 2 equations. Right, so 7 unknowns, 2 equations. I'm missing 5 things. Now, because the degree of freedom of this is 1, if I am given one motion, one dot, one term with a dot on it, I should be able to find all of the terms. If I'm given one term without position, I should be able to find all the others. So I'm given that. I'm given that the position theta is pi, 180 degrees. So I should be able to find all of the, I should be able to find r, because I'm given the speed, which is a single dot term. I ought to be able to find all of the terms that have single dots. And because I'm told that the speed is constant, that's a double dot term, I should be able to find all the double dots. So what I'm thinking now is that I ought to be able to find other equations that will tell me r, r dot, r double dot, theta dot, and theta double dot. If that's the case, then I'll have only two unknowns left, c and p, and everything will work out just fine. So what I'm going to focus on now is trying to find relationships between the motions that were given to me and all of these r's and r dots. Okay, so first thing I do is I say, well, they give me the fact that it's moving on a path, so I'm going to write those equations down. So first thing I know is that r is equal to 0.6 times theta. Okay. Then I can easily take a derivative of that, so that r dot is equal to 0.6 theta dot, right? And then I can take another derivative, r double dot equals 0.6 theta double dot. Okay, so now instead of 2 equations, I now have 5 equations. So I'm sneaking up on it. I'm also told that the speed is constant. So I'm going to write down the speed in r theta directions. The speed, the velocity, is equal to r dot in the ur direction plus r theta dot in the u theta. Alright, so the speed then is going to be the square root of r dot squared plus r theta dot squared. And they tell me that that is equal to 2. Okay, so now if you count the number of equations, I've got 6, 2 forces, 3 for the r's and r dots, and then I have the 6th one is speed equals 2. I need one more since I have 7 unknowns, and the last thing that was told is that the speed is constant. So if I'm going to do this by hand, at this point I would put it into Mathematica. I'll show you that. I'll post the Mathematica solution as well. But if you were going to proceed by hand, what I want to do is find the 7th equation by taking the derivative of the speed and saying it's equal to 0, because the derivative of a constant is 0. Now, because of the square root sign, that would be kind of clumsy to do. So what I'm going to say is if the speed is constant, then the speed squared is also constant. So what I'm going to do is take the derivative of speed squared. So let's do that. So we'll call this, I'm not sure what to call it, but anyway, we'll call it Q. So Q is going to equal speed squared. So that's equal to r dot squared plus r theta dot squared. That's speed squared. And I'm going to take the derivative of Q, speed squared, with respect to time. So this is going to be 2 r dot r double dot. Well, actually, I've paused for a minute, thought about this. Because Q has two variables in it, it might get a little confusing. So what I'm going to do is eliminate one of the variables from Q, and then I'm going to take a derivative. The way I'm going to do that is I'm going to use these equations for R and R dot and put it in there for the Q. So let me just back up a little bit. I'm going to erase this. Not that it can't be done that way, but a little bit easier, I think, to see. Okay, so Q is equal to R dot. I have an equation for R dot, which is 0.6 theta dot. So this will be 0.6 theta dot squared. So that's R dot squared. Plus, then I have an equation for R, which is 0.6 theta dot. All of that is squared. Okay, so now I only have one variable. So then I'm going to take the derivative of Q with respect to time. So when you do, what you'll end up with is, let's see, I guess you could probably expand this, but anyway, we'll take the derivative. 2 times 0.6 theta dot times the derivative of what's inside, which is 0.6. The derivative of theta dot is theta double dot plus, bring the power down, 0.6 theta dot times, then we have a product formula on the inside. Okay, so that is the derivative of Q, or the speed squared, and since it's constant, this has to equal 0. Okay, so essentially now it's a matter of solving all of these equations and just being very careful. The way I plan to do it, if it was completely up to me, I would just take all of these equations and shove them into Mathematica. But if you don't want to do that, then what I will do is I will take the equation for speed. This one, let me change the color. So, alright, so what I'm going to do is take this equation right here and solve it. What I'll do is I will take the relationships for R and R dot, which are right here and here, and take those guys and put them in there for R and R dot. That will give me one equation, and the only unknown in there will be theta dot. So I'll be able to solve for theta dot. Alright, so combining those guys will get me theta dot. So I have theta dot. Then what I will do is go down here to the equation for dq dt. And if you notice, the only thing that's in there is theta. Yeah, there's theta in there. There's theta dot, and yeah, and theta double dot. So what I'll then do is solve that equation, this one right down here, and I'll get I'll put in the values of theta and theta dot, and I'll solve for theta double dot. Okay, it's just simple calculator type stuff. So once you have the theta double dot, then I can come up here and get the R dot, and the R double dot. Right? I'll just come back in, plug numbers in, and I'll get the value of R, which you can do right now. I mean, theta is equal to pi, for example. and then once I have the number for theta dot, I'm going to here get r dot, and I'll get the number for that. And once I have the number for theta double dot, I'll just plug into here, and I'll get the r double dot. So that gets me, now I'll have the theta dot, theta double dot, the r dot, the r double dot. I can go up to, let's see, I had the equation for beta, for psi, excuse me, which I've already gotten, I guess. Yeah, okay, so I've already gotten the psi, so I know the beta. Beta is 90 minus psi. So then I'll come back up here to these equations. I have my r's, I have my r, I have my r double dot, I've got the theta dot, I have the r dot, the theta dot. So I have all of these numbers, so I can get the right hand side completely. I've got the beta, so it's 90 minus 72. So beta is 90 minus 72.3. So I know the beta. So the only thing, I've got the m and the g obviously. So the only thing that's left are these two equations for c and p. Okay, so what I'll do then is just go ahead and do the number crunching, and I'll give you the values that I come up with for each of these. So I'll pause it until I'm ready with the numbers. Okay, so what I did was plugged into the formula for Q, which was right here, because it had nothing but theta and theta dot in it, rather than this one. Rather than using that one, I'll use this one down here. The speed squared is 16, because the speed was equal to, oops, I'm sorry, put in the wrong number, so it should be a speed of 2 squared is 4. I put in the wrong number, so hang on a second. So I'm getting theta dot of 1.01. So out of this equation I get theta dot equals 1.01. So let me pause and then I'll go get the rest. Okay, so now I took my theta dot and I put it into this bottom equation right here, this one, to solve for theta double dot. I just plugged in the values that were known. All of them are known except theta double dot. I end up with a theta double dot of a negative 0.295. So I now have my theta dot, and my theta double dot. So I'll pause and calculate the next values. I'm going to get r dot, and r double dot next. Okay, so here I just plug in the angle theta equals pi, and I find that r is equal to 1.88. Then I have the theta dot, and so I just multiply by 0.6, and I find that r dot is equal to 0.607. And then finally I plug in the theta double dot that I have, multiply by 0.6, I end up with r double dot is a negative 0.177. So now I have my r dot, r double dot, theta dot, theta double dot, and all my angles. The only thing that's left is to plug into the equations, or the force equations, and solve for C and P. So I'm going to do that next. I'll pause and come back with the solution that I have. Okay, so I took all of these values and I put into the two equations with the C cosine beta and the P, and I solve for C and P, and what I get is my C is equal to a negative 0.88. The negative means that I drew it incorrectly, so I'm showing that the circular slot is pushing the peg away from it, but it's actually going to be pulling inward. No big deal. I probably should have known that because the acceleration is always inward from the on the path. Anyway, and then the value of p that I get is equal to a positive 3.92. And it's positive, meaning that that I'm right in the direction that I thought it did. Was I thought the slot actually pulled it up. So in other words, it's resting on the bottom of the pink pin. So that's the solution for this one. If you notice, the process was essentially the same. It was just a little bit more tedious on trying to solve it. And as I mentioned, I'll prepare the same thing with the derivatives and everything using Mathematica, and I'll post that as well.